In this section, we'll study neural networks. Let's recall the perceptron, Adeline, or logistic regression is the simplest artificial neuron that makes decisions by weighting up evidence. Look at the figure. This is input vector having 3 features. Weighting up the feature values, we can get a net input. Based on the value, now the decision will be made. Of course, the weight values will be computed through training. Now, this simplest artificial neuron can be used as building blocks to organize more complex neural networks, as in this figure. And this simplest one is a building block to get such complex neural networks. In machine learning, a black box model refers to a model whose internal workings and decision-making process are difficult to understand, even for the developers who create them. The neural networks are mostly black box models. Their accuracy may not be better than other algorithms for tabular data sets, and their accuracy may not increase with more hidden layers. Okay, here we have input layer, and there are 2 hidden layers, and this is the output layer. And sometimes just one hidden layer is the best model. If you try to add more layers, then the accuracy is becoming worse in many cases. Also, here for tabular data sets, so far your data set is in metric, and each row is a data point, and collection of this data point is your data set. In this case, the data set is in a tabular form. For most of this tabular data set, neural network is not better than other algorithms such as logistic regression and support vector machine, KNN, and some random forest algorithm. Here, we'll see a simple network to classify handwritten digits. Handwritten digits are collected from MNIST, and handwritten digits first will be segmented to get these images, and each one has 28 by 28 grid pixels, and after segmentation these are collected. And so we call the data set here MNIST data set. Is a modified subset of 2 data sets collected by NIST, U.S. National Institute of Standards and Technology. The first set contains 60,000 images. And this first set will be used for training, and the second set is 10,000 images for test, so that when people are developing some neural network algorithm, including deep learning algorithms, this data set is used. So everybody is using the same training data set and same test data set, and we can compare the accuracy improvement and try to get better algorithms. So it is used a lot once. Okay, for this data set, a simple neural network can be made in this way. There is one hidden layer having 15 units, and the input layer has 784 neurons, is 28 times 28 is 784. So each pixel point is considered as a feature, so that the dimension is 784, and we put 15 of them here in the hidden layer. And now there are 10 digits, so that we have 10 units on the upper layer. Okay, that is a simple neural network for handwritten digit classification. Now, once we formulate a neural network, then what the neural network will do, that's the question. So for example, in the figure, the first output neuron will try to decide whether the input is 0 or not. And for the second one, and this will decide whether the input is 1 or not. Okay, so we focus on this one. Now, here people understand this neural network in this way. For example, in a hidden layer, this layer is try to see if the component, the value in a certain area of the image. And the next one is another area, and focus on another area, try to find some different values, and again, another area, so that all combined to make here the value 1, ideally, and everyone else over there is 0, then we can decide the input is 0. So people understand in this way the neural network, but in fact, it's a little bit wrong. I spent a long time to understand this neural network, and I guess I'll try to explain later on and what really happened. But anyway, an intuitive explanation can be made in that way. Anyway, for each one, now for this neurons in hidden layer may focus on certain area to recognize the component of the number. Okay, so that is explanation. And in the hidden layer, and the first neuron may focus on this portion, and second, third, fourth neurons, for example, now here try to understand these regions. So all together combined, now we'll get this 0. So that's one explanation earlier people considered. So it is not easy to understand how it is working. Now, for solving in training, usually people try to use gradient descent method, so that the objective function, the cost function, can be organized at the output layer. The activation is made, and compared with the label, we try to minimize this cost function. And by using gradient descent method, we update W in the training step. Now, there are 60,000 images, and each one has 60,000 because there are 10 digits. And this is huge. Once you try to use this all data points, then it's too much. And by using all 60,000 images you update once, then it's not a really good idea. So that rather than such the update strategy, we may try to update more frequently by using small portion of the data set. One good idea is, in fact, the mini-batch algorithm. For example, and you may choose about 30 or 40 subset, and by using that one, you may update once, and next 30, you can update once more, and then you are trying to go through whole data set. And in this way, you can update. That is called mini batch update. Okay, so we choose M training point, and which is way smaller than original number of data points. By using M, the images you can update once, again. Here, once you go through in training, go through whole data set, then we say we finished one epoch, but one update is one iteration. So for this 60,000 the images, if you are using, for example, 10 images in each iteration, then you have to do 6,000 iterations to cover all data set, whole data set. So after finishing here 6,000 iterations, you finish one epoch. And for an epoch, we shuffle the data set and random sorting. And for each M samples from top, and we update the W and the bias using the mini batch, the gradient method, so that after finishing one, to access all data points, we can say we finished one epoch. And if it is required, then we can go to another epoch. But the number of iteration is much more than the epoch. But when you are using the logistic regression, then we are using all the data points in one iteration, so that one iteration is the same as one epoch. But for this large data set, definitely you have to access the data points along with a mini batch algorithm, so that number of iterations is very high, but your epoch may not be high. Okay, here we have a realization in programming. So it is implemented by Michael Nielsen. He looks like a very good programmer. He implemented this algorithm. It's a complete algorithm. And this is written in Python 2, so that in modern society, right now, without changing and many portions, you cannot run it. However, I'll try to show you this implementation. Okay, let's go down. This is almost all functions are included here. Now, many of the lines is for explanations. Some here, now doc strings are given. Now, however, look at over there, and that end with 116, which means that you can implement a neural network within around 100 lines. The Python is so powerful and flexible, so that you can finish this implementation around 100 lines. Here, and import this loader is written separately, so that altogether I can say that your implementation can be done within 200 lines. Now, and here we have MNIST loader, load data wrapper, so that by using that, here training data and validation data, test data, I separate out, and 5,000 among 60,000 training data set, I use only 50,000, and for 1,000, for 10,000, I use this the images for validation during the iteration. And now by seeing the second set, the train set having 10,000 images, I tested. And here the neural network is designed. In input layer, 784 units, and hidden layer has 20 units, and our output layer has 10. If you want to add another hidden layer, then you can put over there another number. Then you can make a network having 2 hidden layers, quite flexible. Even with this small program, you can do, you can design and you can organize a very flexible network. Now here, numbers. The maximum number of epoch is 30, and batch size for mini batch update is 10, and now eta is 30.0. That is running rate, because we put here in formula and divided by n number of the data points so that your running rate can be large. So that I chose 3. Okay, here by using the stochastic gradient descent along with the batch size 10, so it's a mini batch algorithm, and now executed. This one is executed. Here we see the validation accuracy. After 1 epoch, already around 90% of accuracy. And after 30 epochs, and here we have a little bit better than 94% accuracy. Now slowly increasing. We have accuracy comparison. If you are using support vector machine in default, from the scikit-learn, the default support vector machine has such accuracy, almost the same as this, the simple neural network. If you well-tune the support vector machine, then you can achieve up to 98.5%. And also, this convolutional neural network, CNN, which is a deep learning algorithm. Once you design well convolutional neural network, then you can get 99.79% accuracy. Only 21 is missing. And in this case, it's a machine, the CNN, is arguably better than human. Look at here. These are the images missed by the CNN. Now, can you understand what it is? Somehow, people are writing the digits in this way. So all of this here, and it's not easy to understand. None of them is recognizable. But also quite similar images, similar writing, the machine can understand very nicely. So for this data set, in fact, well-designed CNN is way better than human eyes. So that's the reason once you design well a deep neural network, then we can enjoy very high accuracy. Here we have a model of deep neural networks, that all the complexity be learned automatically from data. Now, earlier, we dealt with only tabular data sets. That is, in fact, future vectors. But now we try to use images or sound signals, and from that one, inside the algorithm, automatically future will be extracted, and then that'll be used through the neural network. That kind of neural network is called deep neural networks. So future extraction is done automatically from the data. Simple algorithms can perform well for some problems. So in machine learning area, you may think this one. Rather than very sophisticated algorithm, you may try to use simple learning algorithm with good training data. Then you can enjoy better accuracy. Here, there is some deep learning packages known in the society. Keras is made very early time. In fact, that is the same year as TensorFlow, 2015. It's a high-level artificial neural network application program interface API. It can run on top of TensorFlow, Theano, and now here CNTK. Keras focuses on being modular, user-friendly, and extensive, written in Python. It has the longest history, so currently Keras is most popular. TensorFlow is low and high API levels and an end-to-end open source deep learning algorithm by Google. It's a symbolic math library used for neural networks so that it's faster. And however, TensorFlow is difficult to use and debug. And the software is written in Python, and C++, and CUDA. And once you install the required, the necessary the background programs, then you don't have to worry about the C++ and CUDA. Just by using Python, you can do that. But anyway, TensorFlow is a little bit more difficult than the Keras, and also in use and also in debugging is more difficult. Now, another program is PyTorch, is developed and a little bit later, and here 2015, but that's 2017 by Facebook. And then later on here, some PyTorch Foundation is now take the program. It has outstanding community support and development, and PyTorch is much easier to use and debug than TensorFlow. It's written in Lua, but you don't have to worry about it. Everything can be done along with Python. And here we have a summary for those packages. And you do not need to learn C++ or Lua. Currently, Keras is most popular due to its simplicity and long history. And also, it is made user-friendly, so it is quite easy to use. Now, PyTorch is most rapidly growing right now. It can be viewed as a trade-off between Keras and TensorFlow, and it's between Keras and TensorFlow. It is particularly good for natural language processing applications. Mathematicians and experienced researchers will find PyTorch better than Keras for many applications. So I recommend you to learn about PyTorch. And PyTorch is a really wonderful algorithm. Okay, that's the end of section.